So in the last lesson, we introduced boundary layers and a bunch of parameters that were important for boundary layers. Velocity profile inside the boundary layer, what the boundary layer actually was. In other words, this line that is defined to be 99% of my upstream flow velocity. So that defines my boundary layer. Have equations for boundary layer thickness, have equations for shear stress acting on the plate, equations for drag force. Unfortunately, that only told us half the problem, because something I failed to mention was that everything in the previous lesson only has applicability to when this boundary layer is laminar. There's also a situation where this boundary layer could be turbulent, and so that's what we have to deal with today. So the condition for the boundary layer to be laminar or turbulent is based on the Reynolds number. If the Reynolds number is less than roughly 500,000, the boundary layer will probably be laminar. And so everything that we saw in the previous lesson applies when the Reynolds number is less than 500,000. However, if the Reynolds number is bigger than 500,000, the boundary layer will most likely be turbulent. And so in that case, what happens is, remember that my Reynolds number is velocity times length over kinematic viscosity. So eventually, if my plate's really, really long, eventually this length is going to be really big. So eventually I'm going to end up at a point where the Reynolds number is bigger than 500,000. And at that point, I get this turbulent boundary layer show up. So I have a turbulent sublayer after Reynolds number of 500,000. And so today's lesson is going to be what happens in this region when the boundary layer is turbulent. And so we're going to want to know the similar parameters. So boundary layer thickness for this guy, velocity profile inside there, drag force, shear stress, things of that nature. The same stuff we derived for the laminar case in the previous lesson. So in the previous lesson for the laminar boundary layers, some of those equations, some of the parameters could be found mathematically, analytically. In the turbulent case, that's not the situation here. All these equations are determined experimentally. So experimentally, we have a velocity distribution that looks like Vx over u is y over delta to the 1/7 power. So we have this 1/7 power relationship show up from the experiments. Boundary layer thickness, 0.16x over Reynolds number based on x to the 1/7 power. So again, x is starting at the front edge of the plate. My position down that plate, just like in the previous case. Shear stress coefficient, C tau, 0.027 over Reynolds number to the 1/7 power. Again, based on location, so that's going to change based on where I am along the plate. And then force coefficient. So again, this is integrated over the entire plate length. So I have my Reynolds number based on the entire plate length. In this case, 0.032 over that Reynolds number to the 1/7 power again. And again, in the laminar case, there was two ways we could calculate either the overall force or overall shear stress. There were general equations, and then from those equations, we backed out a shear stress coefficient and got equations for those. And that was the method that I like to use. So the first thing you want to do is find the Reynolds number. Second thing, find the coefficient. Then third thing, find either the shear stress or force. For the turbulent case, that's the only way to do it, which is, again, why I like that method when I did the laminar example. So in this case, find the Reynolds number. First thing you want to do, again, that's the first thing you want to do anyway, because that tells you whether it's laminar or turbulent. So you basically need to do that first. Once you have that number, stick it in the equation for C tau. Then at that point you can find tau or F using the same equations we had from before. So those equations we saw on the previous board were again determined experimentally. It turns out that there's better equations for higher Reynolds numbers. Again, determined experimentally. So the previous equations we just saw are pretty good between 500,000 and 10 million. But above 10 million, it turns out there's better approximations, and that's given by these formulas here. So my C tau, 0.455 over natural log of 0.06 times the Reynolds number based on where I am, whole thing squared. That gives a better approximation for higher Reynolds numbers for the shear stress coefficient. Similarly, for the force coefficient, I have 0.523 over natural log of 0.06 times the Reynolds number based on length in that case. Again, whole thing squared on the bottom. So those give better approximations for the turbulent boundary layer at higher Reynolds numbers. So depending on whether it's higher or lower than 10 million, either use the previous ones or these ones. Now, one big catch about these equations is that coefficient of force, for example, I'm taking over the entire plate, but as we saw when I developed this turbulent boundary layer, the turbulent boundary layer isn't necessarily over the entire plate. The drawing I had, it showed up down the plate at some point, and so really that would only cover that part of the plate. If I want the entire plate, I'd have to do something else, and so that gets a little bit tricky if the boundary layer is not at the very beginning. So if boundary layer is fully turbulent from the very beginning, these equations and the ones in the previous board will work pretty well, and that is actually possible, but not probable in nature. So nature usually has the picture that I drew before, where the boundary layer shows up later. So you're going to need to know what to do in that case as well. So if I have a boundary layer that's fully turbulent from the leading edge, so right at the very beginning, I don't have any laminar boundary layer, all it is purely turbulent. That's also called tripped. So again, it can do stuff to make this happen. You can put little things on your plate. You can kind of make the flow be turbulent even from the very beginning. So in that situation, all the previous equations are perfectly valid. However, again, normally in nature, what happens is you start off with this laminar boundary layer, and then at some point where the Reynolds number is roughly 500,000, you get this turbulent boundary layer show up like we had before. And so generally, unless the question says that the boundary layer is fully turbulent from leading edge or tripped, so unless one of those two statements shows up, you have to assume that we have this situation, and so this situation need a few new equations. Well, actually only one new equation for the force, because if I want the boundary layer thickness, that's just a laminar boundary layer thickness. This gets a little confusing because at this point, are we talking about this thickness or that thickness? So it's a little unclear. Again, for shear stress, at this point, shear stress on the plate, this can just be the laminar portion, that can just be the turbulent portion, but then when I go to calculate the force, I need the entire thing, and so that's the one I'm mostly concerned about. Also, I'm mostly concerned about force in general, the drag force. So for the mixed case, I need the force equation. So to derive that, what we're going to do, easiest way to do that is kind of take this situation. So I'm going to assume that my entire boundary layer is turbulent, use the force from that, and then take away this front part because that's not turbulent in the mixed case. So I'm going to start with this, then take that part away, add the laminar part back on, and that's going to give me this mixed case. So doing that, we get the equation for force for this mixed situation. And what we get in that scenario is that my force coefficient, CF, is 0.523 divided by natural log of 0.06 times the Reynolds number based on length, whole thing squared. So this is basically my entire turbulent part. And then I'm taking away this front part, but the front part I know what the Reynolds number is, so that just basically becomes a number that I need to take away, and then add back on the laminar part. But again, the laminar part from 2 lessons, or from last lesson, the laminar part, I know that Reynolds number as well, so that's just another number. So I end up with, number ends up being 1520 divided by that Reynolds number based on length. So that is my mixed case force coefficient. So as a review of all the boundary layer equations, I like to have this big table giving me all my important parameters based on Reynolds number, what the boundary layer thickness is, local stress coefficient, drag coefficient, velocity profile for all 3 cases, laminar, turbulent, and mixed. So laminar, Reynolds number less than 500,000. I have that as my boundary layer thickness, shear stress coefficient, drag coefficient, and velocity profile, all from the previous lesson. Then from today's lesson, in the turbulent case, 500,000 to 10 to the 7th, we have this boundary layer thickness, stress coefficient, force coefficient, and velocity profile. And then the better approximations at higher Reynolds numbers for stress coefficient, and force, because those are the things we're usually concerned about the most. So those are the important things at higher Reynolds numbers. And then in terms of mixed case, again, all I really care about is force. So I have this force coefficient that we just saw previously. So this nice table sums up all the equations we're going to need for boundary layer questions. So time for some examples. First example, have air at standard conditions flowing over a smooth flat plate at 30 meters per second. Flat plate's 3 meters long and 1 meter wide. Want to know what the total force acting on this plate is. So my solution, I'm going to follow my standard 3-step procedure. Find the Reynolds number, find CF, and then find the force. So first step, find my Reynolds number based on the entire plate length. So Reynolds number is velocity times length over kinematic viscosity. So velocity of 30 meters per second. Length, again, in the previous question and the previous lesson, mentioned about how when there's two dimensions, one is the length, one is wide. Length is the one we want here. That's the way the air is flowing. So the length of 3 meters is the one we want for the Reynolds number. And then kinematic viscosity of air at standard conditions, back of the book, 1.5 times 10 to the negative 5 meters squared per second, gives me a Reynolds number of 6 million. Now 6 million is bigger than 500,000, so we're in the turbulent case here, but the problem didn't say that the boundary layer was fully turbulent from the leading edge, didn't say that it was tripped. So because it didn't say that, I can safely assume that the boundary layer is going to be a mixed boundary layer. So the equation I want to use for my CF is the mixed equation. So finding that CF value using the mixed equation 0.523 divided by natural log of 0.06 times the Reynolds number, whole thing squared, minus 1520 over that Reynolds number. I know that Reynolds number is 6 million, so just plug that in. 6 million down there, 6 million down there. Gives me a force coefficient of 0.00294. These are generally in the 0.002 or 0.003. So generally that range is kind of what you're looking for anytime you do this. So now that I have that, find my value of F. So force is 1/2 CF rho U squared A. So 1/2 0.00294. Density of air, standard conditions, 1.2 kilograms per cubic meter. Velocity, 30 meters per second, square that. And then my area, 3 meters by 1 meter. Again, the question stated that it was flowing over. So over, I can assume that's only over and not under. So only one side of the plate, only the top side. So my entire area is just 3 square meters. Gives me a drag force of 4.76 newtons in this case. So I follow up to that previous question. Assume the boundary layer was mixed. In other words, it has a laminar part and a turbulent part. What I want to know now is how much of that overall drag force that we found, the 4.76 newtons, how much of that comes from the laminar part and how much of that comes from the turbulent part. The way I can figure this out is going back to my picture. I have a flat plate, laminar boundary layer to begin with, then a turbulent boundary layer shows up later. So the portion that is attributable to the laminar part is that portion there. The portion that's attributable to the turbulent part is that portion over there. So I can find, or I need to find, how much of this, so what is that distance that the laminar portion of the boundary layer is acting. So I want to know what this value XC is. XC I know is defined to be where the Reynolds number is 500,000. So rearranging the equation for Reynolds number, I can find my value of XC to be mu times the Reynolds number divided by my velocity. I know my Reynolds number is this 500,000. So my kinematic viscosity from before times 500,000 divided by my velocity of 30 meters per second gives me this length to be 0.252 meters. So basically the first 25 centimeters of my 3 meter long plate has a laminar boundary layer. The rest of it is turbulent. So to find the laminar force, basically what I can do is pretend that instead of this plate being 3 meters long, I'm going to pretend it's only 25 centimeters long, because if it was, that's exactly the force that it would have. So with that, I can get my force coefficient. I know my Reynolds number at the end of this 25 centimeters is 500,000, because that's how I got that number to begin with. So my coefficient of force in that scenario is 0.00188. And then plug that in to find my force. So 1/2 that number density 1.2, velocity 30, area 3 times 1 gives me a laminar force of 0.26 newtons. So that's the laminar contribution to my overall drag force on this plate. Then now that I know that, the turbulent contribution is fairly simple. I know that my total force is the sum of the laminar part and the turbulent part. That's the only two things I have. So those two things have to add to the total. I know my total is 4.76. I know my laminar contribution is 0.26. So to find my turbulent portion, just take my total, subtract away that laminar force we just found. So 4.76 minus 0.26 leaves me with 4.5 newtons, which must be the turbulent contribution. So another example, modern submarines use towed hydrophone arrays to listen to enemy submarines. So assuming I have a hydrophone array, assume it's a flat plate operating behind my submarine, I want to know what the drag force is acting on this array, 5 meters long, 1.5 meters tall. Assuming I'm in Arctic waters of cold water, fresh water, 5 degrees Celsius. For two cases, one a velocity of 0.1 meters per second, and second case a velocity of 1.0 meters per second. So same solution procedure. I want to find my Reynolds number, then find the CF value, then find the force. So I can do kind of both parts A and B at the same time. So for my Reynolds number, I have a velocity times length over kinematic viscosity. So for part A, my velocity is 0.1 meters per second. For part B, it's 1.0 meters per second. Length is 5 in both cases. Kinematic viscosity of fresh water, 5 degrees Celsius, found in the table, back of the book. 1.52 times 10 to the negative 6 meters squared per second. Gives me a Reynolds number of 329,000 for part A. So that's less than 500,000. That's going to be laminar. For part B, gives me a Reynolds number of 3.3 million. That's bigger than 500,000. So that guy is going to be turbulent or mixed. And again, because nothing in the problem said anything about it being fully turbulent from leading edge or tripped, I'm going to use the mixed value for CF in that case. So step 2, find my CF values. Again, part A is the laminar version, 1.33 divided by the square root of the Reynolds number, 329,000 in this case. For the turbulent case, or mixed case, I get 0.523 over natural log of 0.06 times the Reynolds number squared, minus 1520 over the Reynolds number. So that gives me, for part A, the slower speed, 0.00232 for my force coefficient. For the faster one, 0.00306. So now last step, find the force. Force is 1/2 CF rho u squared times area. So again, for my laminar case, I have 1/2 my laminar CF, 0.00232, density of water, 1,000 kilograms per cubic meter, my velocity 0.1 meters per second squared. Then the area of that flat plate is 5 meters long, 1.5 meters high, but in this case it has two sides, front side and back side, so multiply that area by 2 because it's on both sides. So overall drag force on that guy, 0.174 newtons in the slow case, part A. Same thing for part B, but now I have my turbulent value of CF, 0.00306, and my velocity of 1.0 meters per second squared gives me a drag force in that case of 22.9 newtons.